complexity.
All right, girl. Who do we want to be today? You'll be the Wildcats. Rawr. Oh, that's cute. You know, the precocious girl with pigtails, I think. Ooh. Oh, my Laura Croft persona. Oh. That's a good one. No, I just think I'm gonna send my tall avatar self today.
Are you ready to meet?
Be right there.
Is that the best you can do?
You are so critical. Just a minute.
That's not much better.
Be with you two momentarily.
What did you say you were doing in my truck that night we came here?
Life used to be so simple, and all of a sudden it's so complex.
Complexity. Now there's a topic.
Yeah. How do you start with something so simple and end up with life being so complicated?
Like you said, everything starts out simple. Jeeves, if you please.
Whether you're talking about dog stars or dog stars, diamonds or diamondbacks, all normal matter is made from electrons and two other tiny little guys called quarks. Put those three things together, let them interact, and you get all the incredible complexity that makes the universe such an interesting place. But how does that happen? How do you get somebody like Leonardo da Vinci from mixing just 3 different particles? How do you go from such simplicity to such incredible complexity? Let me take you on a journey, and together we just might figure it out. Along the way, we will probe life, consciousness, and the inner workings of the human brain, and just maybe uncover a few surprises. We begin our journey in the world of the small. Basic particles are really, really tiny. For a long time, people thought these particles had no size at all. But then along came quantum mechanics, which proves it is impossible for anything real to have a size of 0. Today we know that fundamental particles have a real size, called a Planck length, named after Hall of Fame physicist Max Planck. Now a Planck length is so small it's hard to imagine, much less to describe, but that won't keep us from trying. If a Planck length were as large as a grain of sand, then a proton would be the size of the Earth. And an atom would be the size of the orbit of Jupiter. That single grain of sand would be almost as large as the whole Milky Way galaxy.
Isn't a Planck length about 10 to the minus 33 centimeters?
Yes, it is. Hard to believe the redhead didn't understand that.
What redhead?
You mean Kevin didn't tell you?
Never mind. Play.
Look at these grains of salt. To the naked eye, they all look the same. But under a microscope, you can easily spot the differences. But every electron in the universe is absolutely identical to every other electron. If we could magically swap every electron in your body with some other electron, there would be no change. You would still be you. When you try to picture the behavior of things this small, you might resort to some really weird science.
Quantum mechanics.
Some really smart folks thought this stuff up, and they made it clear that these fundamental particles don't always behave as you might think they would. Describing an electron is like describing dice at a crap table. There's a 50% chance that the electron will end up here, and a 50% chance that it's there. In 1927, Werner Heisenberg had some new ideas about uncertainty. He said,
For an electron, the more precisely the position is determined, the less precisely the momentum is known, and vice versa.
Einstein thought he was nuts, but the more scientists played with that notion, the more they concluded that subatomic particles can disappear and reappear in another place, and they can do this without existing in the intervening space. When an electron is trapped inside an atom, the places that this activity is limited to is the space around the nucleus, and this makes it look like a shell. Basic particles can also be in more than one place at a time, if the time is brief enough. An electron can travel from here to there along all possible paths simultaneously. And even more astounding, these particles can appear out of the nothingness of space, exist for an extremely brief instant, and then disappear. Scientists call them virtual particles. They may be virtual, but they can have very real effects. It's all this jumping around that makes particle descriptions so inexact. But then existence itself is inexact at these tiny scales. You know, time doesn't exactly behave itself on tiny scales either.